Now, the next time you're on a passenger jet, just look out the window. You'll probably watch the flaps smoothly extending right before landing, and honestly, it looks completely effortless. But beneath that sleek aluminum and composite skin, well, there lies a sprawling, incredibly complex network of mechanical engineering. Today, we're doing a full explainer on this hidden anatomy of an aircraft. We're going from the cockpit all the way to the control surfaces.
Okay, let's dive into this by looking at a core physics problem. Say a pilot in an An-26 wants to pull the nose up. They pull the yoke back exactly 200 millimeters. Now, how does that relatively tiny human-powered movement actually muscle a massive elevator surface against literal hurricane force winds? It's an absolutely incredible sequence of mechanical translation. To really wrap our heads around this translation, think of the airplane as a living, breathing organism. Just like us, it has a brain where decisions are made, it has a nervous system that rapidly transmits those signals across long distances, and of course it has powerful muscles that do the actual heavy lifting. The overarching layout of an aircraft perfectly maps out these exact pathways, connecting the cockpit up front to those complex aerodynamic surfaces in the back and on the wings. Right, so our journey begins in the brain of the aircraft, the cockpit. Now, the yokes and pedals in here, they are way more than just steering wheels. They're the primary sensory input devices. They act as the very first translators, taking a pilot's physical intention and instantly converting it into a mechanical signal. When the pilot pushes those pedals up to 100 millimeters either way or turns the yoke 90 degrees, they're kicking off a mechanical cascade that has to travel flawlessly through the entire length of the fuselage. And that signal, it travels right through the aircraft's mechanical nervous system. Engineers build this out of rigid control rods. We're talking incredibly lightweight but super strong thin-walled tubes made from duralumin, steel, and titanium. Now, to make sure the pilot isn't, fighting the friction of the machine itself, literally every single joint in this system is packed with tiny ball bearings. They even use flexible jumpers across the moving parts to ground the whole thing into a single electrical mass that totally prevents any dangerous static electricity from building up. But here is where we hit a massive engineering hurdle. Imagine this. You've got this metal rod moving back and forth, carrying the pilot's commands. It starts in the nice, warm, pressurized cabin where everyone is sitting, but it has to travel all the way out into the unpressurized tail section, where the air is super thin and the temperature is just absolutely freezing. So how in the world do you pass a constantly moving metal rod right through the wall without venting all your life-saving cabin pressure straight into the stratosphere? And this brilliantly illustrates the magic of pressurized lead-throughs. These are specialized little nodes built right into the pressure bulkheads. Inside them, the control rods pass through layers of really tight rubber O-rings and felt seals. Think about that for a second. The pressurization of an entire passenger cabin relies completely on these tiny rubber rings maintaining a dynamic, airtight grip on a moving piece of metal. It's wild. If we map this out on the framing of a fuselage, the pressurized zone is securely isolated between specific frames, so the control rods run smoothly right under the floorboards. And at the exact moment they exit the pressurized zone to reach the tail, bam, they pass right through those hermetic seals. This ensures not a single drop of that precious cabin pressure is lost to the outside sky. Okay, moving from the brain and the nervous system, we finally reach the muscles. Because let's face it, moving a massive control surface against hundreds of miles per hour of wind resistance requires some serious force. In lots of systems like the flaps, the pilot's mechanical or electrical signal meets heavy-duty hydraulic power. This is exactly where the aircraft flexes its true strength to manipulate those immense aerodynamic forces. So, what does this actually look like in action? Let's walk through the exact rapid-fire sequence of deploying the flaps on an An-26. Step 1. The pilot flips a switch on the center console. Instantly, an electrical signal snaps open the electrohydraulic valves. Highly pressurized hydraulic fluid rushes in, releases a friction brake, and spins up the hydraulic motors. These motors then forcefully rotate a long transmission shaft running down the back of the wing, which finally cranks the heavy ball screw jacks to shove those multi-ton flaps straight down into the rushing air. Now, what's really interesting about this data is the sheer speed and the built-in redundancy of the whole setup. When commanding a landing configuration at a steep 38-degree angle, the The main hydraulics can muscle those flaps down in just 14 to 17 seconds. That is incredibly fast. But check out the emergency failsafe. If the main hydraulics ever fail, a backup system takes over immediately. It pushes fluid through shuttle valves. Sure, it takes a little bit longer, around 20 to 30 seconds, but it guarantees the flaps are going to deploy, making sure the aircraft can land safely at the right speed. I mentioned ball screw jacks just a moment ago, and we really have to zoom in on this microengineering marvel. To push a flap down against immense wind pressure, you can't just use standard screw threads. The sliding friction would be way too massive. Parts would just jam up or even snap. Instead, engineers use a threaded shaft and a nut completely filled with tiny rolling steel balls. As the shaft turns, the balls circulate continuously. It totally replaces sliding friction with ultra-smooth rolling friction. Honestly, it's the only way to reliably move that kind of massive weight under such extreme loads. But, with all these incredibly powerful forces at play, we absolutely have to talk about safety mechanisms. Let's just imagine a terrifying what-if scenario for a second. The tail of a plane has an elevator that controls the pitch, moving the nose up or down. And that elevator is actually split into two halves, a left and a right. What would happen if, deep in the mechanical nervous system, something slipped and one half of the elevator moved just a few degrees more than the other while flying at hundreds of miles per hour? Well, without synchronization, you're looking at a complete disaster. If one half catches more air than the other, the plane is going to violently roll without you even commanding it. It puts immense twisting stress on the tail structure and completely destroys your pitch stability. And that, right there, is exactly why aircraft feature mandatory elevator synchronization. With synchronization in place, you get symmetrical deflection, perfectly even load distribution, and crucially, a safe and stable flight. So, to guarantee this synchronization, engineers use some seriously clever fail-safes. They don't just leave the left and right halves to do their own thing. Oh no, they are physically locked together using rigid mechanical shafts, torsion tubes, or highly calibrated gear transmissions. This literally means if you move one, you physically force the other to move the exact same amount. And in modern fly-by-wire systems, this has evolved to use electronic sensors that constantly monitor the exact microposition of both halves, using a computer to make absolutely sure they move in perfect lockstep. There's another brilliant safety feature we need to highlight, and it's called artificial feel. Think about it. When you have huge hydraulic systems or electronics doing all the heavy lifting for you, the pilot can totally lose the natural physical sensation of the air pushing back against the plane. To fix this, engineers install what are known as load feel springs. These are heavy-duty springs built right into the control columns that physically push back against the pilot's hands to artificially mimic that aerodynamic load. So the crucial point is that this tactile feedback protects the aircraft and everyone on board. On the N-26, for example, if a pilot violently shoves the yoke forward to push the nose down, they could induce some really catastrophic negative G-forces. But the very moment the pilot pushes the yoke past a 6-degree downward deflection of the elevator, these heavy load feel springs kick in hard. They suddenly create this massive physical resistance in the control column, physically stopping the pilot from pushing any further into the danger zone. When you step back and really look at this entire anatomical tour beneath the floorboards, it just puts everything into a new perspective. The pilot's physical intention is translated through duralumin rods, it bypasses hermetic seals, and flows straight into hydraulic muscles. It really is thousands of hidden, interconnected parts all moving together in perfect harmony. We've literally traced a gentle 200mm pull of a yoke all the way back to the deployment of a multi-ton flap. It kind of changes how you experience flying, doesn't it? So the next time you look out that airplane window and see a flap smoothly pushing against the rushing wind, will you think about the spinning motors, the pressurized seals, and the countless steel balls working tirelessly just out of sight? I know I will. Thanks for joining me on this explainer, and keep looking out those windows.